All right, now, as far as rational goes, for f of x is equal to 1 over x, we get this general form. Now, end behavior. As x goes to positive infinity, what is f of x going towards? F of x is going to 0. This is actually a huge concept in pre-calculus and calculus, where we're moving towards 0. Are we ever going to get to 0? It never gets there. That's the thing, is it's never going to get to 0. What happens when x goes to negative infinity? As x goes to negative infinity, what's x going towards? Or what's f of x going towards? It's going towards 0 again. Is it ever going to get there? How about this? As x goes to 0, from the negative side. So if I'm on the negative side, this right here is the negative side, this right here is the positive side of my graph. So if I'm going towards 0, if x is going towards 0, which means this, I'm heading that way. If I'm heading that way, where am I heading towards? F of x is heading towards negative infinity. And what if I'm going towards 0 from the positive side? So that means I'm in the positive side and I'm heading towards x equals 0. I'm going towards f of x is going towards positive infinity. So even though this isn't really end behavior, it kind of is, because we're talking about the end behavior of the graph. Because there's 4 different ends. There's 2 ends to each branch. So we can start talking about the different end behaviors just by looking at where my x's are going. My x's can go to infinity, but they can also go to the idea of, all right, right here, that's an asymptote at x equals 0. And I do want to introduce another idea. This is a non-mathematical way of doing things. But what I like to do is I like to call them the problem childs, or the problem children. And I refer to them as the problem children, and you need to find them out, and you need to figure out exactly what they are, because this is going to be a key to everything that you do. And the problem children are values of x that make the denominator 0. Because that's where we're going to have a lot of the issues that we run into. Now, for example, if I have f of x is equal to 1 over x, if I set x equal to 0, or if I set the denominator equal to 0, this is a problem child. And that's going to lead me to the idea that, all right, my x's can never be equal to 0. And the cool thing is, you can instantly, as soon as you find that problem child, go right to the x-axis and draw a vertical asymptote. Because if x makes the bottom 0, can I divide by 0? No, it'd screw up the entire function, wouldn't it? And we don't want to screw up the function. We kick out the values that screw up the function and we don't use them. So if I know x equals 0 is bad, I kick it out and I draw my asymptote right there. Because in the original graph here, here's my vertical asymptote. So when we do our analyzing of the graph itself and we're trying to figure out domains and ranges, the first thing you always do is figure out what the domain is. And the domain, you always start with all real numbers, and then you kick out the problem children. Now, a different one. F of x is equal to 1 over x minus 2. This is what the directions would look like, and this is what they're actually trying to find mathematically. What is the value of x that makes f of x undefined? Now, here's the... I'll let you write that for a second, and then we'll talk about the line of thinking that I want you guys to use in your head. I want you guys to think, all right, what do I have to do? If I'm looking for values that make this undefined, what do I do? And it's a great flowchart. And what I like to try to do for you is to break it down as simple as I possibly can. And here's about as simple as it can possibly be. All right. I want f of x to be undefined. So f of x is undefined. And since I'm in a flowchart, I'll make nice little circles there. Now, you tell me, what's the only way that f of x could be undefined? Well, actually, there's two ways. And I'll give you the first one. The first one we really don't run into. There's no value of f of x. There just isn't. We can't plug it in. We don't use it. So, like, if we're talking about how many cupcakes you have to make in order to sell this amount of money, you're not going to talk about negative cupcakes, right? Because can you make negative cupcakes? Not in this universe. So we don't worry about negative cupcakes, that type of thing. So that's kind of like we boot those guys out of the we kick that out of the domain. So if we're dealing with like negative cupcakes, well, negative cupcakes don't work. If we're talking about a negative speed, well, a negative speed can actually work. But if I tell you, if the problem says, well, how far is it to Denver, and you say negative 27 miles, that's wrong. That's not, we don't, it'd be 27 miles. It wouldn't be negative 27 miles, because we don't measure stuff in negative distances and things like that. But if f of x is undefined, we can't divide by 0. So this is kind of, the first one that I did is kind of like the more of the restriction idea, where we can't have like negative numbers. But this one is the math idea. You can't divide by 0, so set the denominator equal to 0, solve for the x's. And those are your problem children. Especially when we're dealing with a rational expression like this, and then you kick those guys out of the domain. So, in this example, 1 over x minus 2. And it asks for what makes this undefined. I say, well, this is a fraction, right? It's rational. Rational means it's a ratio, so it's a fraction. It's a ratio of polynomials. I have 1 over x minus 2. Well, what would screw everything up? If x minus 2 is equal to 0, f of x is undefined. Because you'll get f of x is equal to 1 over 0. Do we want that at all? No. So I just say, all right, well, x minus 2 is equal to 0. Add a 2 to both sides, so I say positive 2 is equal to positive 2. X is equal to 2. Two is my problem child. Now for here, 0 was my problem child. For here, 2 is my problem child. Actually, what all we did was we moved the graph over to 2. So I have I get a vertical asymptote. Let me move that up a little bit. At x equals 2. And then we draw the same graph, which is really nice. And I'm going to stop that video here.